we have been solving assignment number 3 and we have solved problems up to number 5. So, here we will be solving problems from 6 up to 10th. The sixth problem says, suppose there is a two-dimensional world where it is seen that all the charge put on the conductor comes to its surface. So, in the two-dimensional world it will be like a disk, and if you give a charge here, it is all coming to the surface. It gets distributed on the surface. So, let me show that by red. Let us say this is positive charge. It all comes on the surface, and since there is a symmetry, circular symmetry or cylindrical symmetry, all the charge will be uniformly distributed. Following the argument given in lecture 26 at 5:11 minutes, find the R dependence of the electric field produced by the point charge in that world. Now, you see, if this is a conductor, field inside has to be 0. So, argument we are going to use is, suppose I look at the field at a point shown by this dot and make a cross section here shown by pink on the two sides. Now, if the field is 0 and the charge is uniformly distributed, the dependence of the electric field should be such that the field anywhere inside is 0. So, let us say this point, which is at a distance r 2 from the bigger section and r 1 from the lower section, the field is 0. Field is going to be 0. Now, all the distances are the same. So, field is going to be 0 if they cancel from each other side. If this angle is theta, then the charge on the smaller side is r 1 theta times whatever, let us call it lambda is the charge density. Charge on the other side is going to be r 2 theta times lambda. Now, if the R dependence of electric field, let us say, is 1 over r raised to n, then the field at this point in the middle is going to be r 2 theta times lambda over r 2 raised to n minus r 1 theta lambda over r 1 raised to n. The only way this can become 0 is if n equals 1, and this implies E should go as 1 over r. Keep in mind that in the three-dimensional world, E goes as 1 over r square. Now, how do I realize this two-dimensional world? It is very simple. Suppose I take a long cylinder, infinitely long cylinder, in which the third dimension anyway gets integrated out. So, essentially for electric field it becomes a two-dimensional world, and I know indeed there the field goes as 1 over r. Next, I am going to solve problem number 7, which says there is a point dipole which is put inside a cavity in a conductor. So, I have a conductor of arbitrary shape and make a cavity inside and put a dipole here, a point dipole. The surface charge density on the surface of the cavity, which I will show by green, is sigma 1, and outside it is sigma 2, and the net charge inside is q 1, net charge outside is q 2. What is true about sigma 1, sigma 2, q 1 and q 2? So, let us look at the field produced by this point dipole. I am going to remove this dipole, put a point here where it is, and the field lines are going to be something like this. Here they will close on themselves, here they will come in, and here they are going to close on themselves. So, if I look at the surface out here and make a very small box, keep in mind that field inside the metal is 0. The net flux through this small box is going to be non-zero, and therefore, sigma 1 is non-zero. Certainly, sigma 1 is going to be on this side, it is going to be negative, and on this side is going to be positive on the lower side, but it is non-zero. However, if I look at a Gaussian surface inside the metallic flux, of this Gaussian surface is 0, because there is no field, number 1. Number 2, the net charge on a dipole is also 0. Since the charge enclosed by this Gaussian surface is 0, dipole already has a net charge 0. So, that can only happen if q 1 is also 0. So, what is happening is that inside this cavity green surface, the surface of the cavity inside has a distribution of charge, positive and negative charge. That means, sigma 1 is non-zero. However, sigma 1 is such that the net charge integrates to 0. What about outside? Now, you see, if I look at it, so here is the inner cavity, here is the point dipole. Field out here is 0, net charge enclosed here is 0. So, that outer side total charge q 2 will also be 0, because the cavity is neutral. So, if there is no charge taken on the inner surface, outer surface also has 0 charge. There cannot be any charge distribution inside the metal. So, anyway, in the bulk metal there is no charge, charge comes only on the surface. So, outside charge is 0. Can this 0 charge be distributed? That means, can I have sigma 2 not equal to 0? Suppose I did. So, there was some positive charge somewhere, and consequently, since net charge is 0, there has to be some negative charge somewhere else. And therefore, what will happen in this case is there will be a field line going from positive to negative charge. And that means, work done in taking a charge from positive to negative charge will be non-zero. However, a metallic surface is always a constant potential surface. Therefore, if I will go from inside the metal or conductor, work done is 0. So, it cannot happen that if I come from the outer side, there will be some work done, and from the inner side work done will be 0, because it is a conservative field. The only way it will not happen is if there is no separation of positive and negative charges, and therefore, sigma 2 outside is also 0. So, the answer in this case would be sigma 1 is non-zero, however, q 1 is 0, sigma 2 is 0, and q 2 is also 0. Next, problem number 8. An insulating spherical shell of inner radius r 1 and outer radius r 2 carries a uniform polarization. So, we have a shell of inner radius r 1 and outer radius r 2, and it carries a polarization p. The bound surface charge sigma 1 theta on the inner surface and sigma 2 theta on the outer surface are to be found. We know bound surface charges are nothing but p dot the normal, p dot the normal. The normal on the inner surface is pointing inside, because normal is away from the volume, and on the outer surface normal is pointing out. So, sigma 1 theta is going to be p, which is p z, times normal, which is pointing in the minus r direction. So, this is going to be minus p cosine of theta. Sigma 2 theta on the other hand is going to be p z dot r, because it is radially out, which is going to be p cosine of theta. So, the bound charge on this cavity is going to look like what I show in the figure. On the inner surface, it is negative on the theta 0 onwards and positive on the lower side. On the outer surface is the other way, p cosine theta is positive on the upper hemisphere and negative on the lower hemisphere, with the dependence being given as p cosine theta. Next, we solve problem 9, which is asking for the electric field in the dielectric shell of problem 8. So, we have already solved problem 8, where we have found that the charge is plus on this side and minus on this side with cosine theta dependence, this charge I know gives me an electric field in the opposite direction E, which is going to be minus P over 3 epsilon 0 z. What about field due to the inner cavity? The inner cavity has a charge which is negative on the upper side and positive on the lower side. So, it has a dipole moment going down, and this dipole moment will give a dipole field. So, the additional field is going to be due to dipole of dipole moment P, which is 4 pi by 3 r 1 cubed P z in the opposite direction of z. Another way of looking at it is, if I have this cavity which has this hole here, I can think of this as if it is a cavity with uniform polarization, which I will show by red, and added to it is an additional polarization in the negative direction inside this cavity. So that the two polarizations inside the sphere of radius r 1 cancel, and there is nothing. So, electrically I can think of it like this, and this I know gives me a field E. The uniform polarization gives me a field minus P over 3 epsilon 0 z plus a field due to this the negative polarization sphere, which is precisely this field. So, that is the answer. Finally, we solve question number 10, which is electric field inside an insulating cylinder which has a polarization in the x direction P is equal to P x will be. Now, this is very simple, because P x means there is a surface charge, there is no bulk charge, but the surface charge sigma is P dot S, because S is n, which is P cosine of phi. So, what we have in this is positive charge on the positive x axis and negative charge on the other side, and therefore, I can see that field is going to be in the negative x direction, and since this is a two dimensional thing, so E is going to be minus P over 2 epsilon 0 x. So, that is the end of assignment 3.